Hi, this is video 3 of the Surface Engineering Lab Demonstration Series. In this video, we will look at elemental depth profiling of materials using GDOES, which stands for Glow Discharge Optical Emission Spectroscopy and is commonly referred to as GDS for short. This technique is a combination of plasma, optics, and a database. The plasma used in this machine is a glow discharge and is the same as the plasma discussed in video 1 of this series. To form this type of plasma, it is necessary to have an anode, a cathode, and a low pressure. In this GDS, the cathode, which is this copper plate, and the anode, which is this internal hollow rod, are isolated from one another by a ceramic sheath. Samples are placed here and therefore are in direct contact with the cathode and subjected to a cathodic potential. When we want to analyze samples, the vacuum pump is started and this rod pushes both the sample and the sample insulator towards the machine. With the help from an O-ring, a seal is created from the outside atmosphere, therefore making pumping down possible. Evacuation is carried out until a desired vacuum is reached, before remaining contaminants from the air are purged by flushing through some argon gas. Once purging is complete, a specific pressure of argon gas is built up in the machine before the power is switched on. When the power is switched on, the ionization of the argon gas forms a glow discharge plasma inside the sealed chamber containing the samples. Once the plasma forms, the argon ions are accelerated towards the sample surface, and this bombardment causes fine removal or etching of the sample. Over time, this removes the surface layer by layer, thereby allowing depth profiling of the samples. Atoms in the material that are etched away are ionized or in an excited state. Relaxation of these high-energy atoms back to the ground state releases characteristic photons. An opening in the back of the GDS directs this mixture of photons towards a lens, which in turn focuses this light onto a diffraction grating. This diffraction grating then acts to scatter this light at different angles depending on the wavelength of the photon. Photomultiplier detectors that are strategically placed at specific angles that correspond to expected wavelengths for different elements measure the intensity of this light as it arrives. As the sample material is removed layer by layer over time, the intensity of light that each detector records changes with time. If the sputtering rate is known, then the speed of material removal is also known, and therefore the depth with time can be calculated. By using calibrated databases, it is possible to give quantitative information on the elemental composition through the material. Reference or standard material, which are materials with well-defined, homogeneous and known compositions, help to create databases. Since these materials give reliable and accurate light intensity readings for their composition, it is possible to build calibration curves for the expected light intensity to composition for each element. By using many reference samples with varying compositions, it is possible to build databases for comparison with sample data. If comprehensive calibration curves are set up, then quantitative data can be obtained. However, in most cases, these databases are only semi-quantitative. GDS elemental depth profiling has many advantages, including 1, the ability to give very quick results within a few minutes, 2, the ability to give quantitative information, 3, the ability to measure most elements, including light elements such as nitrogen, which can be problematic for other techniques such as energy dispersive X-ray spectroscopy, or otherwise known as EDS or EDX. And 4, the ability to depth profile non-conductive materials by changing from a DC source to an RF power source. However, as with any machine, there are several drawbacks. These include 1, the fact that it is a destructive technique, and so, as you can see here, it creates an etched away crater on the surface of the sample. 2, due to the need for a flat crater base to give an accurate depth reading, depth profiling is limited beyond 100 microns because of rounding of the base. And 3, due to contaminations such as oxides or grease on the surface of samples, and the delay for stabilization of the plasma, the first 100 nanometers of the GDS depth profile can be inaccurate. As a result of the already mentioned qualities of GDS elemental depth profiling, it has found many applications in the automotive, electronic, aerospace, and steel industries, and is commonly used for measuring the thickness of coatings or the chemical composition of new alloys or castings. Additionally, it is also widely used in research and development labs, like those found in universities, such as this one.